For factoring polynomials with complex zeros, we're going to be able to keep going after the stage where maybe previously we would have said that a polynomial was prime. If we look, for example, at this polynomial right here, 3x cubed plus 27x, we can start trying to factor it by old techniques, which would mean that maybe we'll look for a GCF first. We see that 3x is a common factor in both terms, so I can factor out that 3x, which leaves me with just x squared plus 9. Now, by our old factoring techniques, such as factoring trinomials, factoring a difference of squares, we would have called a sum of squares prime, and we would have stopped here, saying that we couldn't factor it any further. Now, however, we're going to be able to factor everything down to linear factors regardless of its form, and the way we do that is we start by finding the zeros. Well, if I can't find the zeros by factoring, then I'll find them from some other method instead, which means I'm going to start out by just setting this expression equal to 0 and solve it by whatever method applies. In this case, the square root method looks like a good choice. So I will subtract 9 from both sides, and then I will take the square root of both sides, giving me x equals plus or minus the square root of negative 9. Now, of course, the square root of negative 9 is an imaginary number. This gets me x equals plus or minus 3i in this case. But it still does get me complex zeros, and using the factor theorem, we can get from complex zeros to factors that may have complex coefficients. So think of it this way: if x equals 3i is a 0, then the factor theorem tells us that x minus 3i is a factor. If x equals negative 3i is a 0, well, that tells us that x plus 3i is a factor. So I can construct this polynomial back by creating these factors from the known zeros. I don't want to forget about this factor 3x that I found first, but I'll go ahead and put my whole factored form as 3x times x minus 3i times x plus 3i. Now for the zeros, I've found two of them. I found 3i and negative 3i. But there's one more. I don't want to forget about this GCF right here. If I were going back to the idea of solving a polynomial equation by factoring, I would set each factor equal to 0, and then dividing both sides of this by 3. 0 divided by 3 is, of course, still just 0. So this does also have 0 as one of its zeros. We can continue now with another example. This here is a difference of fourth powers, which we don't have to recognize as a difference of fourth powers right away. We can start out just recognizing it as a difference of squares. A difference of squares would factor as a product of conjugates, meaning a product of two factors that are exactly the same as each other except for the sign. So I'll have a plus in the first and a minus in the second, and I fill them in by asking myself what I would square to get each of these terms. To get 16x to the fourth, I would square 4x squared, so I will put that as the first term in both factors. And to get 81, I would square 9, so I'm going to put 9 as the second term in both factors. So we have factored this by a very standard technique of factoring called the difference of squares formula. And looking at this, we can see that the second factor is a difference of squares again. So this will again factor as a product of two factors with a plus in the first one, a minus in the second, and otherwise identical. 2x is what I would square to get 4x squared. 3 is what I would square to get 9. So this part of the polynomial is factored completely, But the first part is again a sum of squares, which is just like the first example we saw. This is not factorable by our traditional techniques. We need to find the zeros, and from those zeros, construct the factors. So we will start by setting this equal to 0, and then solve the equation by whatever method is appropriate. Again, the square root principle seems to be a good choice here. So I will subtract 9, divide by 4, and then take the square root of both sides, getting me plus or minus the square root of negative 9/4. I can apply that square root independently to the numerator and denominator, which gets me x equals, since this is a negative number inside the square root, this is going to be an imaginary result, plus or minus 3/2 times I. So I'm now going to, like I did in the previous example, construct factors from these zeros. X equals 3/2 times I gives me the factor x minus 3/2 I. X equals negative 3/2 times I gets me the factor x plus 3/2 I. We can see, however, looking at these, that if I were to FOIL this back out again, my first term would be x times x, which is x squared. But the first term in this polynomial that I was just working with is 4x squared. What happens when we reconstruct factors from the zeros is that we lose a little bit of information, which is the leading coefficient, or what this whole polynomial could have been scaled by. So what I have to do to compensate for that is tack the leading coefficient onto the front of it. Note that I didn't take the leading coefficient of the whole polynomial, which would have been 16. I only took the leading coefficient of the part of it that I factored by this particular method. So I could, if I wanted to, distribute this 4 in parts into these two factors to make them look different. So another way of writing it, I'll put down here in the corner. The cleanest way to do this is to break that 4 up into 2 times 2 and distribute one of those factors of 2 into each of the factors. So that would give me 2x minus 3I in the first factor, and 2x, sorry, that second one's supposed to be a plus, 2x plus 3I in the second factor, or 3/2I, sorry about that. Oh no. Yes, definitely 3I, because the 2 that we are distributing in cancels with the denominator in that 3/2 I. So both of these, either the 4 times this whole thing, or with that 2 distributed into each of these factors, either of these is a perfectly acceptable way to write these factors, but we do need to write our full factored form with both the imaginary factors